A cricket ball hit high into the air accelerates as it falls, becoming a dense 5.5 ounce projectile moving at 60 miles per hour. If a fielder waits for that projectile with stiff, unyielding palms, the ball stops its motion in roughly 2 milliseconds. That abrupt deceleration requires an immense amount of physical force, easily enough to fracture the metacarpal bones in the hand. To survive the catch, professionals use a technique called cradling. As the ball enters the palms, the fielder pulls their hands backward in the exact direction the ball is traveling. The impulse momentum change theorem states force multiplied by time equals change in momentum. Since total momentum change is locked, stopping the ball requires a specific non-negotiable impulse. This leaves force and time on an inverse seesaw. If one goes up, the other comes down, because the required impulse cannot be lowered. A fielder who fails to actively stretch out the duration of the catch leaves the laws of physics to maximize the destructive force on their hands. Scale that exact same physics up to thousands of pounds of metal. Navigating the dense, unpredictable flow of a Mumbai street requires sudden, heavy braking. According to Newton's first law, when the vehicle abruptly stops, the passengers inside continue moving forward at the original cruising speed. Their momentum must be zeroed out. If a passenger hits a rigid dashboard, the collision lasts a tiny fraction of a second. If they hit a deploying airbag, the surface yields, extending the impact over a longer period. This bar chart illustrates the mathematical difference. The dashboard strike creates a massive, instantaneous force spike. The airbag flatters that curve over milliseconds. Stretching crash duration by a factor of 100 directly divides lethal force on the skull by 100. Safety engineers do not build impenetrable fortresses. They engineer specific tools designed to manipulate the timeline of a crash. But mitigating damage requires controlling what happens after the impact. Mechanics categorizes collisions into two types: inelastic, where objects crumple, and elastic, rebounding. While bouncing off a wall might sound safer than smashing into it, physics dictates the opposite. Bouncing requires a complete reversal of direction, meaning the total change in velocity and therefore the impulse transferred is significantly larger. You can clearly see this momentum transfer in a metal Newton's cradle. When a dropping sphere bounces off its neighbor, it transfers its entire momentum through the line, causing the outer sphere to swing violently away. Apply rebounding logic to highway collisions. Decades ago, vehicles were built rigidly to resist physical damage. When they hit a solid obstacle, they bounced backward. That elastic rebound transferred a massive impulse directly to the occupants. Modern vehicles solve this exact problem by utilizing crumple zones. The front end is intentionally engineered to collapse and fold, absorbing the energy and destroying the vehicle structure to prevent an elastic rebound. In a high-speed collision, sacrificing the vehicle to stop the bounce is the only mathematical way to spare the human body from lethal momentum change. While safety engineers use this theorem to mitigate damage, athletes reverse the math to weaponize it. They manipulate contact time to maximize destructive force. When a professional batsman hits a ball, they use a long follow through by extending the time the bat stays in contact with the ball. They apply a sustained force, generating a massive change in velocity. Martial artists use the same principles to strike an opponent. By pushing against the friction of the ground, they create a kinetic chain. This builds rotational momentum from the ground up, transferring it through their hips and into their striking limb. But instead of following through, a karate practitioner will often snap their fist backward the exact millisecond it hits the target. This drastically reduces the contact time of the collision. By intentionally minimizing the time variable, the math dictates a severe spike in the opposing variable. A shorter impact guarantees a maximum burst with destructive force delivered straight into the target. The cricket fielder pulling their hands backward, the automotive engineer designing a collapsing bumper, and the martial artists snapping a punch are all practitioners of the exact same mathematical calculation. Look at this diagram showing momentum units moving between objects. It reveals that momentum operates as the invisible currency of the physical world. This physical currency cannot be destroyed. The only thing you can control is the transaction rate. How quickly that momentum is deposited into a body or an object. Mastering the physical world, whether you are trying to secure a game-winning catch or survive a catastrophic crash, depends entirely on controlling a single fraction of a second.